Now we will start our course of digital electronics. The first topic which we will study in it is binary to decimal conversion. Basically, it's our first topic, which is number system, in which we will study conversions. Okay, so we will study all the conversions like binary to decimal, binary to octal, binary to hexa. These are the conversions from binary to other number systems. And after that, we will, in the second lecture, we will learn from the other number systems to binary, like it's vice versa. So the first conversion we are doing is binary to decimal. So we will take one number of binary, that is 111000, and we will convert it to decimal. Okay, so the number system binary, its base is 2, and for the decimal the base is 10. So now we have the one number of the binary number system, that is 11000, and we will convert it to the decimal number system. So what is the way to convert it? We will use the multiply system, that we will write it as the numbers of the binary, that is 0 multiplied by 2 raised to power 0 plus 0 multiplied by 2 raised to power 1 plus 0 multiplied by 2 raised to power 2 plus 1 multiplied by 2 raised to power 3 plus 1 multiplied by 2 raised to power 4. Basically, we will multiply 2 with it, as we are going from 2 to 10. So we are giving the powers to 2 from 0, 1, 2, 3, 4. The total numbers like 0, 1, 2, 3, 4, like this. And we multiply these our powers with the numbers we have in binary number system. So its value is 0 plus 0 plus 0 plus 8 plus 16. Final answer we have is 24, and this 24 we have is in the decimal number system, and its base will be 10. And to convert binary to octal, okay, when we will go from binary to octal, for this we have the number 1. We are taking the same number as we have for binary to decimal. So now we will see what will we get the result for octal. So for it, the way to do it is, in octal we have the 3 sets, like the set of 3 numbers, this, and for this we will add 1 0 here by ourselves to make it 3. Okay, so now the method will be same whenever we go from binary to decimal, binary to octal, binary to hexa. The way we will use is of the multiplication, not the LCM. This is the way we will use is multiplication. So now 0 multiplied by 2 raised to power 0 plus 0 multiplied by 2 raised to power 1 plus 0 multiplied by 2 raised to power 2. The first set we are using, this is our first set, this is our second set. We will make the set of the 3 digits or 3 bits, we can say 0 0 0. This is our first bit, and the second is 1 1 0. So this is till power 2, and when we will do the second of our set, we will start again from 0. 1 multiplied by 2 raised to power 0 plus 1 multiplied by 2 raised to power 1 plus 0 multiplied by 2 raised to power 2. So the answer we will get is 0 0 0. This is 0, and for this we have is 1 plus 2 plus 0. This is 3. So we will write the final answer by combining the both, that is 3 0. So we will have it is 3 0, and for the base of the octal we have 8. Its base is 8. Like we can we will write it as 3 0, and here we have 8. Okay. So now we will convert. The next thing is binary to hexa. For this we will use in the same method. First of all, the base for binary is 2, and for hexa we have is 16. 1 6 16. So for binary we will take the number 0 1 1 1 0 0 1 1 1. We are taking a bit greater number so we can understand it clearly. We will use the same method, the multiplication method, but the way of doing now the hexa number is that we will make the set of the 4 bits. First 4 bits, then again 4 bits, and the last one we have is the 1. So as we have added one more digit in to make 3 digits in octal, we will now add the other 3 to make in hexa the set of 4. The method is same, the method of multiplication. So 2 raised to power 0 multiplied by 0, and then plus 1 multiplied by 2 raised to power 1, plus the next one multiplied by 2 raised to power 2, plus 1 multiplied by 2 raised to power 3. This is our first set. Its answer is plus 2 plus 0, that is 14. For our next set we have is 2 raised to power 0 multiplied by 0 plus 2 raised to power 1 multiplied by 0 plus 2 raised to power 2 multiplied by 1 plus 2 raised to power 3 multiplied by 1. For this we have is 8 plus 4 plus 0 plus 0, that is 12. And for the last one, 0001, we have is, its answer will be like 2 raised to power 0 multiplied by 1 plus 2 raised to power 1 multiplied by 0 raised to power 2 multiplied by 0 and 2 raised to power 3 multiplied by 0. The final answer of this set is 1. So by combining all of these we have 1, 12, 14. So in hexa number system we have as the values of hexa, we will write it as 1 C E. This is our answer. Where we get from CE, okay, I will explain it on another page. The number we have for hexa are, let me take the another page. Okay, in hexa we have A, B, C, D, E, F. Like these alphabets, we will take them equal to in hexa, only in hexa, okay? So this is 10, 11, 12, 13, 14, 15, and so on. This is which it will continue. So here for the hexa we have 1 CE, like 12 which is equal to C and 14 which is equal to E. The final answer is 1 CE. These are the conversions from binary to decimal, octal and hexa. In our next lecture we will study the conversions from decimal to binary, octal to binary and hexa to binary. In our second lecture we will study the conversions from decimal to binary, octal to binary and hexa to binary. So the first conversion we are doing is decimal to binary. For this we are taking the number in decimal, that is 24 with base 10, and we will convert it to the binary number. So for this we will use the method of LCM, the simple LCM we do in the maths. That is 24, the number we have, and the base of binary is 2 as we know. So we will do the LCM with the number 2. 2 ones 2, 2 twos are 4, the remaining is 0. That is 2 6 are 12, remaining 0. 2 3s are 6, remaining 0. 2 1s are 2, remaining is 1. So this is our final answer. We will write it from here like this: 0 0 0 1 1. You may write it as like this, starting from here, this. So this is how we convert the number of decimal into the binary number system. The next one we are doing is octal to binary. That is octal to binary. The base of octal is 8. We will convert it to the For the numbers in octal, we have the number from 0 to 8. Like we cannot take the whole number 30, that is not the octal number. In octal we have is 3 and 0. But LCM, in this we have the numbers like we can take the 24. So with 2 we have 2 ones are 2 and remainder is 1. With 0 we will have 2 zeros are 0 and of course remainder is 0. So with this we have the final answer, that is 0 0. As we know, we will make the 3 bits as we have studied in the last lecture, so we will add one more 0 here, and to make it 3 bits in octal we have 3 bits always. Okay, so like this we have the final answer 0 1 1 and 0 0 0. Okay, this is our final answer. Now for the conversion from hexa to binary we have, okay, so for hexa to binary we have hexa to binary. We will do this conversion. We will take the number 1, 12, 14 of hexa and we will convert it to the binary. So now we have 1. We will do all these separately. Okay, so for with 1 we will take the LCM with 2, and for 12 we will take the LCM with 2 as we are going into the binary, and for 14 we will do the LCM with 2. So 2 0 and the remainder is 1. Then okay, with 12 we will do the conversion as same we did with the 1. LCM simply 2 6 is 12 and 0, 2 3 is 6, remainder is 0, 2 1 is 2, remainder is 1, and with 14 2 7 is 14, 0 2 3 is 6, remainder is 1, 2 1 is 2 and remainder is 1. So now we will write these. Okay, yes, these are correct. With the as in the hexa we have the bit, we have the group of the 4 bits. So now we will make them 4 to the alphabets which are not 4. First 14, as we have the 14 here, first we will write the number of number of 14. The answer we have, that is 0 1 1. These are the 4 bits, and for again 12 we have the 4 bits. We will write it same as 0 0 1 1, and for the 1 we have 2 in the answer. Now we will complete the 4 bits 00 and then these numbers we have, that will make it 0001, and yes, this is the final answer we have. So these are the conversions we have from decimal to binary, octal to binary and hexa to binary. This is our second lecture. This is our third chapter of our course Digital Electronics. Today we will study the conversions of decimal to number system. Like we will study decimal to binary, decimal to octal and decimal to hexa. So the basic rule we have is whenever we go from decimal to the other number system, we will take the LCM with base of the number system. Okay, so the first we are doing is decimal to binary. Okay, the base of the decimal is the base of the decimal is 10. When we will go to the binary, the base is 2. So the number we have in decimal is 24. Now we will convert it to the binary. We will take the LCM with 2. 2 1s are 2, 2 2s are 4, the remainder is 0, 2 6 are 12, remainder is 0, 2 3s are 6, remainder is 0, 2 1s are 2 and remainder is 1. So our final answer is 1 1 0 0. This is how we go from decimal to the binary number system. Now for decimal to octal, again we will use the same method. According to our rule, we will take the LCM with the base of number system. So the base in octal we have is 8, the base of decimal is 10, and we will take the number 39 in decimal we will convert it to the octal. So 39, and with 8 4s are, and 7 is the remainder. Okay, so our answer is 47. And when we will go from decimal to hexa, we will again use the same method. Sorry, for the hexa the base is 16. Now we will take the LCM with 16. Okay, so the number we are taking is 3296, and we will take the LCM by writing 83296. Like for such big numbers we can use the calculator, and 16, it will be 16206, and the remainder we will have 0. Again by taking the multiple with 12, 16 12, and the remainder we get is 14. You can do it by the calculator. The answer we have is 12, the whole number, okay, 14 0. And in hexa, as we have studied in our last lecture, the alphabets for it we can write it as C E 0 with base 16. This is our third lecture of digital electronics, in which we had studied the conversion from decimal to other number systems. And in our next lecture we will study the conversions from other number system to decimal. This is our fourth lecture of our course Digital Electronics. Okay, in today's lecture we will study the conversion from number system to the decimal, like from binary to decimal, octal to decimal, and hexa to decimal. So to convert the number binary to decimal, the first number we have is 11000 to 10. For this, the rule we have is we will multiply with base of number system. Okay, we will multiply with base of number system, not the LCM multiplication. So to convert this, we have 0 multiplied by 2 raised to power 0 plus 0 multiplied by 2 raised to power 1 plus 0 multiplied by 2 raised to power 2, then plus 1 multiplied by 2 raised to power 3, and plus 1 multiplied by 2 raised to power 4. Now we will write it. The answer we have 16, 8, 0 plus 0, and plus 0. The final answer 16 plus 8, that is 24. The answer we have is 24. This is how we go from binary number system to the decimal. And to convert from octal to decimal, we will multiply with base of 8. We will take the number 47 in octal and we will convert it to the decimal with base 10. So 8 raised to power 0 multiplied by 7 plus 8 raised to power 1 multiplied by 4. That is 32 plus 1, 7. And the answer we have is 39. Final answer is 39 with base 10. Now to go from hexa to decimal, we will use the number in hexa with base 16, C E 0. Now we will convert it to the numbers. It is 12, 14, 0, and now we will convert it to the decimal with base 10. For this again we will multiply it as 16 raised to power 0 multiplied by 0, and in hexa this is our whole number. Like this is not 1 and 4, this is complete 14. So plus 16 raised to power 1 multiplied by 14 plus 16 raised to power 2 multiplied by 12. This is 3072. You can use the calculator for this multiplication. We have a 0. So our final answer is 3296. In hexa we have this. Sorry, in decimal we have this. 3296. We are going from hexa to decimal. Today we will start the lecture 5 of our course Digital Electronics, and our today's topic is logic gates. In this we will study the gates AND, OR, NOT, NAND, NOR, XOR and XNOR. Okay, we will start our topic with the gate, that is AND. The gate AND says that we will multiply our two numbers. Like first we will see its symbol. These are our inputs A, B, and the final output we have is Y, which is equal to A dot B. Simple dot multiplication. So A, B, and the result is Y. We have 0, 0, 0, 1, 1, 0, 1, 1. So by doing the simple multiplication, we will have 0, 0, 0, 0, 1 equal to 0, 1, 0, 0, 1, 1, 1. So we see that we have the final result Y equal to 1 when our both inputs are 1. So this is its, we can say the diagram or the symbol we have, that is like simple D we have to write. Okay. So the next gate is OR, which says the addition process. Its diagram is like this. The arrow, two inputs A, B, the output is Y, which says A plus B, the addition of both inputs. So A, B and final is Y. 0, 0, 0, 1, 1, 0, 1, 1. So by doing the simple addition, 0 plus 0, 0, 0 plus 1, 1, 1 plus 0, 1, 1 plus 1, 1. It says whenever our both inputs are 0, the final result is 0. And whenever any of our input is 1, the output will be 1. Okay, the next gate is NOT, which is basically the conversion. Its symbol is like a simple triangle, and the NOT gate, it makes it, sorry, it will not go inside. Okay, I will draw it again. Okay, like this. This is basically the symbol of conversion. Input is A, output is Y. Input says 0 or 1. The final result we will have is its opposite, 1, 0. It will basically just convert our input. If it's 0, it will be 1. If it's 1, it will be 0. So the next we have is the NAND gate, which says, okay, we will draw it here. NAND is basically, it's the opposite of our AND gate. We will have the NOT with AND, and its symbol will be, these are our inputs A, B. Like this we have the AND. We will draw its opposite, this, and the NOT before the output. So this is Y. We can draw it simply as A, B, the output Y, simple AND gate, and the final Y NOT. B, Y and Y NOT, 0, 0, 0, 1, 1, 0, 1, 1. Simple the results of the AND gate. This is 0, 0, 0, 1. When both inputs are 1, then we have the one simple multiplication of A dot B. Now we will do its conversion. If it's 0, it will be 1, 0 will be 1, 0 will be 1, and 1 will be 0. This is our NAND gate. The next gate we have is, okay, the next gate we have is NOR, which says the opposite of OR. Like the answers of OR, we will convert it, we will make the Y prime. Okay, its symbol is simply OR gate and the NOT before the output. A, B, Y prime. A, B, Y, simply OR gate, and then its conversion that says y prime 0 0 0 1 1 0 1 1. We will apply this 0 1 1 1. Like whenever any of the input is 1, we will have 1 in the output. As we have the NOR gate, this is our OR gate, and now we will apply the NOT on it. This is our NOT, and the y prime, the opposite of the final answer, 1 0 0 0. This is our NOR gate. Now we have the XNOR and XOR gate. We will do it on the next page. Okay, the next gate is XOR, which says basically its symbol or its diagram is like this. Output, 2 inputs. There we have the another line like this. Okay, I will draw it again. Inputs, this, and then this. Okay, the output and the 2 inputs, A and B. Forget it. Okay, A, B, the final result is Y. 0 0 0 1 1 0 1 1. And now for this we have that whenever we have different numbers like 0 1 1 0, we will have the output 1 1 and 1, and the same number will give the output 0. We can write it as y equal to A XOR B. This is XOR. Okay. So the next gate we have is XNOR, which says its symbol is this. Not, and then this. Okay, as we have XOR, now XNOR. Okay, it says that input A, B, and the final output Y, A, B, and Y. 0 0 0 1 1 0 1 1. The output basically says that whenever we have the same inputs, the output will be 1. The opposite of this, XOR's opposite. Okay, this says like 0 0, we have the same numbers, we have 1 1 1, same, we have the output 1, and for the opposite we have 0, the opposite of XOR. Okay, this is XNOR gate. So these are our logic gates which we will use in the digital electronics course. Our next topic of digital electronics is Boolean algebra. We use the Boolean algebra to solve the logical values. Basically, it was founded in 1847 by the George Boole, and we use it in digital electronics to express our data. And we will prove its postulates by using the theorem. Its postulate says that the first postulate is A plus 0 is equal to A. Basically, these are the postulates which we will use and solve our digital electronics data. We will express the data in these by Boolean algebra. So the next is A plus 1 is equal to 1. A plus A says A plus A bar, which is equal to 1, and the multiplication of these are A dot 0 0, A dot 1 is equal to A dot A is equal to A, and A dot A bar is equal to 0. We will use them further, so you will know that why these are the important. A dot B plus C is equal to A dot B plus A dot C. We can prove these postulates This is not a difficult task. I will do one or two for you, and the further you will do it by yourself. A plus A bar B is equal to A plus B. The next postulate is A dot B and the whole prime is equal to A prime plus B prime, and A plus B whole prime is equal to A prime dot B prime. These are our postulates. Okay, we can prove them as we will prove the first one. It says that A and 0, when we will add them, like A plus 0, we will get the result A. Like 0 plus 0, the answer is 0. Sorry, it's A. Okay, our final result. So if we will add 1 plus 0, the answer is 1. You can see that the final result we are having is the A by doing A plus 0, the first postulate. Like this, if we do for the multiplication, we have A 0 and the answer A, which says A dot 0 equal to A. Okay, 0 1 1 0. Sorry, it's 0, it says 0. Okay, A dot 0 is equal to 0. Sorry, it's 0. So whenever we will multiply 0 0 or 1 0, sorry, 0 0 or 1 0, it will give us the final result, which is 0 0. Like this, we can prove the second postulate as well. It says A with the 1, A plus 1 and A dot 1. The results A plus 1 and A dot 1. A plus 1 will give us the 1 and A dot 1 will give us the A. Now we will prove it. We will have 0 and 1. In A, the second input is final, which is 1 1. So A plus 1 will give us 1 and 1. You can see 0 plus 1, 1 plus 1. So this is correct. The second one is A dot 1 is equal to A. 0 into 1, 0 and 1 into 1 is 1. This is also correct, that we will get the output A, and this we will get the output 1. So this is how we can prove these all postulates. Okay, these all are valid and we can prove them. Now we will see one of the examples that why we are studying the postulates in the Boolean algebra. For this, we will take the one example that how can we use it, that is A plus A bar dot B. So now we will simplify it, which says, you can write it as A plus B. That A bar dot B is equal to B. In this we have the three gates which we are using: OR, NOT, AND. We simplify it to the only one gate, that is OR, and we simplified it by using the postulates of the Boolean algebra. We will simplify it in detail that how we converted it. Okay, it will be more easy for you to understand. This is I told you that we converted the three gates. These are 1, 2, 3 gates to only one gate, OR gate, and this is how we did it. We will solve the left hand side of it, that is A plus A bar B. We can write A as A dot 1, as we know A dot 1 is equal to A. So plus A bar B. On the last page we had studied it, that we can write 1 as 1 plus B. 1 plus B was equal to the 1. You can see the postulate, and A bar B, that is A1, we will just multiply it, simply multiplication. A into 1 is equal to A, plus A into B is AB plus A bar B. Now here we are again using the postulate which says that 1 plus B is equal to 1. So A, this is here we quoted 1, okay. So the next postulate we are using is a plus. Simply we will take the b common and a plus a bar, which will be a plus b. This is the postulate we use, that is a plus a bar is equal to 1. So our final answer is a plus b, and this is how we use the postulate to convert the 3 gates 1, 2 and the 3 gates to simplify our expression, and we use the only one gate. Okay, this is where we use the postulate. Now this is simply a bit difficult to use and in our expressions. So now we will study the Karnaugh map, K-map, which is more easy in doing the Boolean algebra. That will be our next lecture. The next topic of our course Digital Electronics is Karnaugh map. In simple, we say it K-map. We can make the K-map, but there are some rules to make it. So first we will study these 7 rules and then we will make the K-map for our practice. The rule number 1 is our group will not contain 0 in it. This is our first rule to make K-map, that says group will not contain 0. We can make group of 1, 2, 4, 8, 16. This is how we make group. These all points will be clear to you when we will make any one of the K-map for the practice. It will be clear to you. This is simply 2 raised to power n. The third rule is each group should be as large as possible. हम ग्रुप को उतना बड़ा बना सकते हैं जितना बड़ा वो बन सकेगा. Group would be as large as possible. The fourth rule is cells containing 1 will be grouped or must be grouped. Cells containing 1 must be grouped. हम उसको कहीं पर भी अगर 1 आ रहा है तो हम उसको छोड़ नहीं देंगे ग्रुपिंग में, वो हर सूरत ग्रुप बनेगा. 1 must be grouped. The fifth rule is groups can overlap. Overlapping of the groups is also allowed in Karnaugh map. The sixth rule is opposite side grouping is also allowed. It will be clear to you as we will draw it. It says basically that this is our K-map. We can make the group like from here to here, the opposite side grouping. This and this, like this, the 2 ones we have. It will be clear to you when we will solve it. The seventh rule is there should be as few groups as possible. That the number of groups should be less. There should not be too much groups. The group must be large, but the number of groups should be less. As few groups as possible. These are our 7 rules which we will use to make the Karnaugh map. Okay, first we will make the K-map for the 2 variable. This is 2 raised to power n. For the 2 variables we have 4. Like we have the 4 boxes. This is how we make the K-map. Our inputs are A and B. This is 0, 1, 0 and 1. These are simply, we can write it anyway, but here we are using the AND gate. So the number 1, by following our rules, this is our group which says A dot B. Our logic gate is using here. You can prove it by AB and A dot B 0 0 0 1 1 0 1 1 0 0 0 1. The next we are doing is for 8 variables, which says that 2 raised to power 3 is equal to 8. In this we will have the 8 boxes. We will draw it as our input A, B and C. 3 inputs we have. You can draw it like this. We will have the 8 boxes like 1, 2, 3, 4, 5, 6 and 7, 8. This is 0, 0, 0, 1, 1, 1 and 1, 0. This is simply the way we write it. So now we can write the any numbers. Whenever you will have the K-map in your exam, these all numbers are filled. The boxes will be filled and you just have to make the grouping. The basic thing is grouping. The number will be given to you. So the first group we will make here is the 1. The second group will be these 2. You can make it in any way, but I am drawing it like this. In the third group I am making all of these. One of the rule is also clear here, that the groups can overlap. This is one group, this is the other group, and they can overlap. Okay, this is our one more rule is clear here. So we can write it as A, this is A, this is B, this is C. See it clearly so it will be clear to you to draw and solve the bigger ones K-map. For 1 is with A, we can write A. Okay, so in B we have 0, so we will write it as B bar. And we have in the first group the C is also representing 0, so C will be also written as C bar. In the group 2, this is our group 2. See it carefully, this is very important. A is the 0. The second group, okay, it's 0. It says A bar, 1 with B, and in C, okay, in C we have 0 and 1, and it's changing 0 and 1. Okay, in group 2 we have the 2 numbers for C. Okay, listen it carefully. We have 2 numbers for C, 0 and 1. The number is changing. Whenever the number is changing, we will not write that. There should be C, but we will not write that. Okay, this is A bar B, simple. And in the third group we have A, B, A, B, A, B, A, B, which is changing continuously to 0 to 1 and 0 to 1, 1 to 1, 1 to 0. The numbers are changing. So once again here we will not write the A, neither B, but we will use the C, which is same in whole, which is 1. C. So our final answer is A, B bar, C bar plus A bar, B plus C. You can see that the K-maps are more easy. Now we will solve for the 16 variables and this topic will be more clear to you. Okay, now for 16 variables, it says 2 raised to power 4, which says 16. It says in this we will have the 16 boxes. 4 means there are the 4 inputs A, B, C, D. The method of writing it is same. 0, 0, 0, 1, 1, 1, 1, 0. Okay. 0, 0, 0, 1, 1, 1, 1, 0. Sorry. Okay, these are the total 16 boxes we have. Now we will simply fill it. We can write here 1, 1, 1, 1, 1, 1, 1. We will take another one here and the 2 ones. Okay. Now we will make the total 5 groups. So it will a little big than these K-maps. So it will be more clear to you. This will be our group 1. For group 2 we are taking these 2. Group 2, this will be our group 3, the whole is the group 4, and this is the group 5. Okay, this one is more clear. Now I will do it again. This is the 1, 1, 1, 1. Okay, and now I will make these groups. See carefully. The first group says this is the group 1. The group 2 is this. This is the group 2. The group 3 is, see carefully. This is the group 3. And now for group 4, we are taking it as the whole. I am using the different color. It will be clear to you. The picture will be clear to you. Okay, this is the group 4, and for the group 5 we are using these numbers. Okay, this picture is more clear. This is the group 5. Now we will write it as, the first one says A, B bar, C bar, D bar. Okay, A, B bar, C bar, D bar. Plus the second group is A, B, C, D. We can see A is same, 0, A bar, but B is changing, 0 and 1. So we will not write the B. And for okay, now for C and D, these are also same. So we will write it as C bar, D bar. For 0 we write the bar. Now for the group 3 is this one. This is the group 3. A is changing, B remains same, B is same, so B. C is same, that is C bar. D is changing, so we will not write the D. The next is group 4. This whole is the group 4 in which C and D is continuously changing. A is changing and just B remains same. So only B is in the group 4. Yes, group 4. And then we will write the group 5, which is this one. This is the red highlight. Sorry, this one. This is the group 5. This box. It says that A remains same. This is A. B is changing. We will not write the B. C is changing. We will not write the C. D remains same. We will write the D. Yes. This is our final answer. So these are our K-maps for the 2 variables, for the 4 variables, and for the 8 variables and for the 16 variables. And we will solve it by giving the power to 2. The important thing is 2 raised to power n. N is our inputs. As we did it, 2 raised to power 2, 4 boxes, 2 inputs, 4 boxes, 3 input, 8 boxes. Yes, 2 raised to power 4, it will be 16 boxes, 4 inputs. These are A, B inputs, A, B, C inputs, A, B, C, D inputs. And these are the number of boxes. So simply this is the rule to make K-map 2 raised to power n. I hope this topic is clear to you. If you have any kind of question, you may ask in the comment section. The next topic of our course, Digital Electronics, is, this is our lecture 8 basically. Now we will study the addition and subtraction. In addition, we will have half adder, full adder. In subtraction, we will also have half subtraction and full subtraction. So we are starting our topic with half adder. So this is half adder, which says that we will have the two inputs A, B, two inputs. We will do the half adder and we will get the result carry and sum. We will have the two results. This is related to the simple addition we do in maths. So A, B, carry, sum. 0, 0, 0, 1, 1, 0, 1, 1. Now we will add them and we will have our results carry and sum. 0 plus 0 is equal to 0. Sum is 0. कोई carry नहीं लिया है, so carry is also 0. 0 plus 1, 1, no carry, 0. 1 plus 0 is 1, no carry, it's 0. 1 plus 1 is sum is equal to 10. 0, 1. As we know, the sum of 1 plus 1 is equal to 10 and the sum of 1 plus 1 plus 1 is 11. Okay, so this is our half adder. Now we will do the circuit diagram for it. In this we have to see our carry, which is the AND gate. You can check it out. 0, 0 into 1, 0, 1 into 0. 1 into 0 is 0, 1 into 1 is 1. And for sum we have the XOR gate, as we have studied it in our previous lecture. So AND gate, we will draw the AND gate with input A and B, A, B, and this is our carry. We will draw the circuit A, B. Now we will draw the XOR gate, and this is our sum. This is how we draw the circuit diagram of half adder. It says that whenever we have the different inputs, the output is 1. And on the same inputs, the output is 0. This is XOR gate, this is its symbol, and this is for the sum, and we have drawn it. This is the diagram, this is the the table we draw for it, and this is the circuit diagram for the half adder. Now we will study the full adder. Okay, this is full adder. In this we have the three inputs A, B, C, and the output is same, carry or sum. Now we will fill these blocks. We have 0, 0, 0, 0, 4, 0, and same 4, 1, 4, 1. 0, 0, 0, 1, 1, 0, 1, 1. And again we will repeat it 0, 0, 0, 1, 1, 0, 1, 1. Now we will do the carry or sum as we did for the half adder. So this is 0, 0, 0 plus 0 plus 0 is equal to 0, 0. No carry, just sum. 0 plus 0 is 0, 0 plus 1 is 1. Again 0 and 1. 0 plus 1, 1 plus 0 is carry 0 and the sum is 1. 0 plus 1 plus 1. In this we will have the 1 carry and the sum will be 0. 0 plus 1 is 1 and 1 plus 1 is 10. As I told you before that 1 plus 1 is equal to 1, 0. 1 plus 1 is equal to 1, 1. 1 plus 1 plus 1 is equal to 2, 1, 0. 1 plus 1 plus 1 is equal to 2, 1, 0. 1 plus 1 plus 1 is equal to 2, 1, 0. 1 plus 1 plus 1 is equal to 2, 1, 0. 1 plus 1 plus 1 is equal to 2, 1, 0. 1 plus 1 plus 1 is equal to 2, 1, 0. 1 plus 1 plus 1 is equal to 2, 1, 0. 1 plus 1 plus 1 is equal to 2, 1, 0. 1 plus 1 plus 1 is equal to 2, 1, 0. 1 plus 1 plus 1 is equal to 2, 1, 0. 1 plus 1 plus 1 is equal to 2, 1, 0. 1 plus 1 plus 1 is equal to 2, 1, 0. 1 plus 1 plus 1 is equal to 2, 1, 0. 1 plus 1 plus 1 is equal to 2, 1, 0. 1 plus 1 plus 1 So this is 1 0. Again this is 0, carry 0, sum is 1, 1 plus 1 again 10, 1 plus 1 is 1 0, and for the triple one we have is 1 1. This is our table for the full adder, and now we will do the circuit diagram for it. And before making the circuit diagram, as we have the 3 bits and the carrier sum, we will first draw the K maps for it, and then we will draw the circuit diagram, so it will be more easy for us. We will first make the K map. So for it we have the 3 inputs, which says that A, B and C. 0 0, 0 1, 1 1, 1 0. And for C we have 0 and 1. Now we will fill these boxes by the help of this table we have. We are making this K map for carry, so we will see the results of carry. When both A and B are 0 and C is also 0, we have 0 0 1 0, 0 1 0, carry is 0, double 1 0, this is double 1 0, carry is 1, for 1 0 0, carry is 0, and for 0 0 1 we have 0, for 0 1 1 we have 1, for triple 1 we have 1, for 1 0 1 we have 1. Now we will make the groups. This is the group 1, this is the group 2, this is the group 3. As we have studied before, we will write this: group 1 AB, group 2 A, B bar, C, and the group 3 is A bar, B, C. Group 1 A, B bar, C, this A, B and C is changing, we will not write that. Group 2 is A, B bar, C. Group 3 is A bar, B and C. Now we will simplify it further. Okay, we are simplifying it further. That says A, B plus C into A, B bar plus A bar, B. We take C as a common. So we have C into A, B bar plus A bar, B. Now to do it more simple, so it will be easy for us to draw the circuit diagram. So we are using A, B and the XOR gate, A XOR B. It is basically the XOR gate. I can prove it here. 0 0 1 0 1 1 0 and 1 1 0 1 1 0. Which XOR gate says? It says that whenever we have the same inputs, the output will be 0. So we can write it now. We will write it as A, B plus C into A XOR B. It will be easy for us to draw the circuit diagram. Now for the sum, you will fill the blocks by the table we draw before. So 3 inputs A, B, C, 0 0 0 1 1 1 and 1 0. For C we have 0 and 1. The results we have from the table are these. So now what this says, there is one more important point. To it we say is checker board pattern. Okay, in checkerboard pattern we have 0 1 0 1 1 0 1 0. Whenever we have this in our K map, we will have the checkerboard pattern. After 1 there is 0 and after 0 there will be 1. So this is checkerboard pattern which says A XOR B XOR C. This is what checkerboard pattern means. And if there are 4 variables, we will add one more D, like this. We will have to add the XOR gate. But now here we have 3 inputs, so this is our expression. Now we will make the circuit for the full adder circuit. First we will draw for the sum, and then after we will draw for the carry. So see it carefully. This is our result of the carry. But first we are doing the sum, so A XOR B, we will have A XOR B. Now we will add the C in it, like this. 2 wires, this is C, this will be A XOR B XOR C. Now for the carry, we will have the A, we will have the B. First we have our AND gate, A dot B, then we have A XOR B with C. So A XOR B and C. There is the AND gate between it. This is C into A XOR B. You can see there is the AND gate between it. Now we will have OR gate between these 2 expressions, this expression and this one. We will have the OR gate here, like this, and this will be our final expression, which says A dot B plus C dot A XOR B. This is okay. Now this is our full adder circuit diagram, our K-map and our circuit diagram. And in our next lecture we will study the subtraction, half subtractor and the full subtractor. Today we will start our 9th lecture of digital electronics. Our 9th topic is subtraction. In this we will study half subtractor and full subtractor. Half subtraction, and we will do the full subtraction. Okay, first of all we will start from half subtraction. In this we have maximum, we have 2 bits, okay, and the possible combination we can have is 2 raised to power n is equal to 4. These are our total possible combinations. So basically we can make its diagram as the first input A, the second input B, the half subtraction as we made for the adder, the same is for subtraction. So borrow and difference. Okay, in this we have 2 inputs A and B and the 2 outputs borrow and difference. So to make it stable, the inputs A, B and the outputs borrow and difference. The inputs are 0, 0, 0, 1, 1, 0 and 1, 1. Okay, when we will minus 0 from 0, we will have the 0 borrow and 0 difference. When we minus 0 minus 1, we will have to take the 1 borrow and the difference will be 1. When we will minus 1 minus 0, the borrow is 0 but the difference is 1. And for 1 minus 1 we have 0 borrow and 0 difference. Now we have to make the K map for it. We can see for the difference, this is our gate, our logic gate XOR, that whenever we have the different inputs, our output will be 1, and for the same inputs output will be 0. This is the XOR gate. So for this we will make our circuit diagram for the XOR, that will be like A and B. We will make our XOR gate symbol. This is the symbol of the XOR gate. We have studied it before. And this is the output A XOR B, and we can say the difference. This is the circuit diagram for the difference. Now we will study the borrow. For this we have to first make the K map, and it will be like A and B. So 0 and 1, 0 and 1. As we have the 4 possible combinations, it means 4 boxes we have. So we will put the numbers in it according to our this one column, the borrow column. On 0 0 we have 0. On 0 1 we have when the A is 1 and B is 0. When A is 1 and B is 0, it is 0. On 0 and 1 it's 1 and again 0. So for this we have the answer A bar because it's 0 and the B because it's 1. A bar B. And now according to this we will draw our circuit diagram. To just get the logic expression, we draw the K map. And for the difference, as we can see, this is the XOR gate A XOR B, so there is no need to draw the K map for it. So now to draw A bar B, we have A. We will take A bar from it. Our NOT gate, it will give us A bar. We have B. This is our B, this is A bar, and then we will have an AND gate. That is A bar B. This is our borrow. Now we will do the full subtraction. Okay, in full subtraction, we will have the 3 bits. So the possible combinations are 8. And we will subtract it till 3 bits. 8 are our possible combinations. So as we have 3 inputs, so A, B and C. This is our full subtraction. And the output we will have is borrow and the difference, as the same for the half subtraction and the difference. Now we will make the table for it. A, B, C, borrow and difference. Zero, 0, 0, 0, 4, 0 and then 4, 1. Then we will have 0, 0, 0, 1, 1, 0, 1, 1. And then we will repeat it again for 1, 1, 0, 0, 0, 1, 1, 0, 1, 1. Now as we minus 0, so it will be 0 borrow, 0 difference. When we minus 0 and then 0 minus 1, we will have 1 borrow and 1 difference. And for 0 minus 1, 1 minus 0, again we will have 1 borrow and 1 difference. 0 minus 1, we will have to take 1 borrow, and 1 minus 0, the difference is 1. So 0 minus 1, 1 borrow, 1 minus 1, 0 difference, and again 0, 1. Okay, now for 1 minus 0, and then we have 1, it will give us 0 and 0. For 1 minus 1 and then 0, we will have 0, 0, and for 1 minus 1 minus 1, we have 1 and 1. Now we will make the K map for it, for the full subtraction. First we will draw for borrow and then for difference. Then for the borrow we have A, B and C, 0, 0, 0, 1, 1, 1, 1, 0 with 0 and 1. We will fill this K map with the help of the above table, and you will get the answers 0, 1, 0, 0. Then we have 1, 1, 1 and 0. Now we will make the groups for it as we did it before. This is the group 1 and then the group 2, and we will take the group 3. Our group 2 and group 3 are overlapping. So we have group 1 plus group 2 plus group 3. It says A bar B plus BC plus A bar C. The answer is A bar B plus we will take the C common from it, and it will give us B plus A bar. Now we will make the diagram for it. Our circuit diagram, it says this is A. We have to take the A bar. So this is A bar after the NOT gate. A bar, and then we have B. A bar and B are connected by AND gate. So this is A bar B. And now we have BC. This is our B. We'll draw the C, the AND gate, and this is B and C. Then we have A bar with C connected by AND gate, A bar C. As we have connected all of them by the AND gate, but we can see that there's also the OR gate is present. Okay, this is not XOR, but I want to say that there is the OR gate is present. Now we have to combine all of these by the XOR gate like this. We have A bar B plus B C, and now same for the A bar C. We will take this in as input and A bar C, and we will combine them with OR gate. So this will be our final answer, which will says A bar B plus BC plus A bar C. Now we will do for the difference. So our K map for the difference is we have A, B and C. Zero, 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 1, 1, 1, 1, 0 and 0 and 1. Okay, so now for difference we will fill this according to our table. You can see the table to fill it. 1, 0 and 1, 0. As we did it before, this is our checkerboard pattern, and what the checkerboard pattern says, it says that we have the XOR gate. A XOR B XOR C. When we have 0, 1, 0, 1, then 1, 0, 1, 0, as the pattern is going on, it is checkerboard pattern. Okay. So now we will draw the XOR gate with A, B and C. It is like A, B, first of all they are connected like this. This is A XOR B. Now we will add the C with A XOR B, C, and it will become A XOR B XOR C. This is our difference, our circuit diagram for the difference. I hope this topic is clear to you. We did the subtraction, the half subtraction and the full subtraction, the K-maps and the borrow and difference. And now we will do one question, that which kind of the question we can get for the K-map or with the half subtraction or the full subtraction. Let's take an example. So this is the kind of question we can get. We have A bar, B bar, C, which means that our A is equal to 1 and A bar is equal to 0. B is 1 and B bar is equal to 0. C is 1 and C bar is equal to 0. And for our easiness, we will write it as A bar is 0, B bar 0, C is 1, 1, 0, 0, 1, 1, 1, 1, 1, 0. Why we are writing these values? It will help us in our K-map. So we have A, B, C. 0, 0, 0, 1, 1, 1, 1, 0, then 0 and 1. We will fill these blocks according to the given question. 0, 0, 1. It means on A, B we have 0 and on C we have 1. 0, 0 and on C we have 1. Here we have 1. On 1, 0, 0. 1, 0, 0. Here we have 1. And on the 1, 1, 1. This is 1 and 1, 1, 0. This is 1. The other values are 0. This is how we fill our K-map. And now we will have to make the groups. This is our group 1. This will be our group 2. And the group 3 will overlap with group 2. Now we will write them as the group 1 values, which is A bar, B bar, C plus A, C bar plus A, B. A bar, B bar, C plus A, we will take the A common from these two values, and we have C bar plus B. Now we will make the circuit diagram for it. This is the K-map, and now we will draw the circuit diagram. Okay, so we have A. First we are drawing the A bar, B bar, C. We will add the NOT gate. It will be A bar. Then we will draw the B bar. And they are connected by the AND gate. A bar, B bar, and we have C with it also. So this C. A bar, B bar, C, they are connected with the AND gate. Now we will draw the A into C bar plus B bar. For first we have to draw the C bar. It will be our C bar, and then we have to take the B, not the B bar. We have to take B. They are connected with the end. No, there's the plus sign. They are connected with the OR gate. This is our OR gate, C bar plus B. And then C bar plus B and A. They are connected with the AND gate. So this is our circuit diagram for the given question. This is A into C bar plus B. Okay. This was our topic of the subtraction, and I did one example for you. So in our next lecture we will study the decoders and the encoders. In our 10th lecture of our course Digital Electronics, we will study the decoders and the encoders. Now we are starting our topic from the decoders. Here decoder is a multi-input and multi-output logic circuit which decodes n inputs into 2 raised to power n outputs. As we have A and B, 2 inputs, so 2 raised to power n means 2 raised to power 2 is equal to 4 outputs. We will write the output as O3, O2, like output 3, output 2, output 1 and output 0. These are 0, 0, 0, 1, 1, 0, 1, 1. These are our inputs, and we will draw the output as on 0, 0. We will have output 0 is 1. On 0, 1, the output 1 is 1. On 1, 0, output 2 will be 1. And on 1, 1, output 3 will be 1. And the other values of the output will be 0. This is how we draw the decoder. We put the values in the truth table of the decoder. You can draw it as A and B, the inputs, the decoder, the 2-bit decoder as we have in the value 2, the 2-bit decoder, and the outputs are 4, 2 raised to power n outputs. Now for to draw the circuit diagram, we will take the O0 value which says A bar, B bar, A is 0, B is 0. For output 1 we have A 0 but B is 1, so A bar, B. For output 2 we have A but B is 0, so B bar, and for output 3 we have A and B. Now we will draw the circuit diagram for it. We will take the A and we will take the B. For A bar B we have the NOT gate. They are connected with the AND gate. And we have A bar and B bar, and by connecting with the AND gate A bar B, that is output 0. Now in the same method we will draw the output 1 which says A bar but B not the B bar, and with AND gate we have A bar B, this is output 1, and for the output 2 we have A and the B bar connected with the AND gate, output 2, and for the output 3 we have A and we have B connected with the AND gate, that is output 3. This is our circuit diagram for decoder, and this is our truth table for the decoders. Now we will see that this is for the 2 bits, and if we have to draw for the 3 bits, like if we have 3 inputs and the 8 outputs, how we will draw that decoder. Okay, now we will see the 3-bit decoder. That is A, B, C, 3 inputs. 2, 3, 2 raised to power n. So the outputs will be 8. 3 inputs and 8 outputs. So as we write for the 2-bit On the same method we will write for the 3 bits: 07, 06, 05, 04, output 3, output 2, output 1 and output 0. Like this we have the 8 outputs and the 3 inputs: 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1. Now we will have to put the outputs, and we will put the output on the same method as we did for the 2-bit. Like we have to put the 1 on its way, we have to draw the 1, 1, 1, and for the output 5, 1, for the output 0, output 1, output 2, output 3, and output 4, then for the output 5, then for the output 6, and then for the output 7. We have to write the 1 like this, and all the other values will be 0, 0, 0, 0. Like you can put all the zeros. And now we will draw the circuit diagram, and to draw the circuit diagram we should know the logical expression. So for output 0 the logical expression is A bar, B bar, C bar. For output 1 we have A bar, B bar, C. Output 2, output 3, output 4, 5, 6 and 7. Total 8 outputs. So for the output 2 we have A bar, B, C bar. Like you can see the output 2, here is the 1. So we have A bar, B, C bar. This is how I am putting the values. So A bar, B, C, A, B bar, C bar. For the output 5 we have A, B bar, C. For output 6 we have A, B, C bar. For output 7 we have A, B, C. Now we will draw the circuit diagram for it, which says like we have to take the A, then the A bar, the B and the B bar, and same as C and the C bar, and they all are connected with the AND gate. A, B bar, C bar. This is our output 0. In the same method we will draw the other outputs. A bar, B bar and the C. We will have the output 1. This is output 0. Like now we will draw the output 2, which says A bar, B, C bar. We will take the A bar, the B bar, sorry, not the B bar, this is B. We will take the B and the C bar and connect with the AND gate output 2. In the same method you have to draw the all outputs. Like you will take the if we have A bar, you have to take A bar, the wire from the A bar, then the B, and for the C bar you will take the wire from the C bar, and for the B you have to take before the NOT gate the B1, not the B bar, and connect them with the AND gate, as there is the AND gate in between. This is the symbol of the AND gate, and you will get your result, the output 1, 2, 3 or whatever it is. Now we will study the encoders. Okay, the encoder is a digital circuit that performs an inverse operation of a decoder. It has two n input lines and n output lines. It is the opposite of the decoder. The second thing is we have the two n inputs and the output will be n. Like if we have 2 raised to power 4 inputs, the output will be, if we have 2 raised to power 2 inputs, like 4 inputs, the output will be 2. We can draw it as the 4 inputs of the decoder D0, D1, D2 and the D3. But there will be the 2 outputs. It is our encoder and the output will be A and B. It will be the opposite of the decoders. So now we have to draw a truth table which says that A and B 0, 0, 0, 1, 1, 0, 1, 1. Now we will write the 1 on the same method as we did before this, and the all other values will be 0. Now to draw its circuit diagram, we have to write it as A is equal to the value of A and the value of B. Now we will put its values as, we have the 1, this one of the A and this one of the B. And on these values we have 1 in D2 and D3. So its answer is D2 plus D3. Now for the B we have this one and this one. On this value where we have 1, it's on D1, and for this one we have 1 on D3 plus D3. These are the values for A and B. Now we have the inputs D1, D2, D3. The only inputs which are getting involved in our expression, D1 and D3 are connected by the OR gate. This is D1 plus D3. This is B for the B, and now for the A we have D2 connected with the OR gate D2 plus D3. Okay, this is the circuit diagram. This was our truth table and this was our decoder. As we draw it for the 4 inputs and the 2 outputs, we can also draw it with the 8 inputs and the 3 outputs, the opposite of the decoder. The 11th lecture of our course Digital Electronics is memory devices. In this we will study the memory devices. For this lecture I will record the lecture in Urdu language so it will be more clear to you. इंग्लिश में हमारे पास जगह जगह पैराग्राफ और एक्सप्लेनेशंस लिखी हुई हैं, उसका कोई फ़ायदा नहीं है एक थ्योरी की चीज़ को इंग्लिश में एक्सप्लेन में करती हूँ. हम इसे उर्दू में डिस्कस करेंगे. अगर कोई भी कंफ्यूजन आए आप लोग कमेंट सेक्शन में पूछ सकते हैं. अब मेमोरी डिवाइसेस हम स्टार्ट कहाँ से करेंगे. पहली चीज़ क्या होती है हमारे पास स्टोरेज. स्टोरेज क्या है, कुछ भी ऐसा जहाँ पे कोई चीज़ स्टोर की जा सके. ठीक है ना, सिंपल सा लफ्ज़ है स्टोरेज. अब स्टोरेज डिवाइसेस हमारे पास कौन सी हैं, इसमें हमारे पास डिवीजन आएगी, एक प्राइमरी एक सेकेंडरी. ठीक है, प्राइमरी होगी रैम और रोम और सेकेंडरी हमारे पास होंगी कोई भी पेरिफेरल डिवाइसेस. अब पेरिफेरल डिवाइसेस कौन सी होती हैं ये हम आगे जाके इसको डिस्कस करेंगे. इधर हमारे पास इम्पोर्टेंट बात क्या है कि जी हमारे पास जो सेकेंडरी स्टोरेज होती है ये परमानेंट होती है. अगर आप इसको सुनने के साथ साथ अपने पास लिखते जाएंगे तो आपको ये ज़्यादा अच्छे से क्लियर होता जाएगा. सेकेंडरी हमारे पास परमानेंट होती है उसके बाद क्या चीज़ है हमारे पास मेमोरी, ठीक है। सिंपल कंप्यूटर की जो मेमोरी है इसकी हमारे पास क्लासिफिकेशंस आएंगी। एक होती है हमारे पास इंटरनल प्रोसेसर मेमोरी, ये क्या है ये आगे जाके मैं इसे एक्सप्लेन करूंगी, अभी मैं जस्ट ऊपर से टॉपिक बता रही हूँ, फिर हम इसे अच्छी तरह इन डिटेल डिस्कस करेंगे। उसके बाद हमारे पास है मेन मेमोरी, ये क्या है हमारे पास इसमें दिस इज वन, दिस इज टू, मेन मेमोरी दिस थिंग, रैम, रोम। रैम में हमारे पास मजीद दो टाइप्स हैं, डायनेमिक रैम, स्टैटिक रैम। रैम रोम की मैं अलग से एक वीडियो बनाऊंगी, छोटी सी वीडियो होगी, उसमें रैम रोम की सारी बात हो जाएगी। द थर्ड इज सेकेंडरी मेमोरी, ठीक है। ये तीन तरह की मेमोरीज हैं हमारे पास। अब हम इधर एक छोटा सा पॉइंट रोम का देखेंगे कि वो क्या कर रहा है। कुछ चीजें अंदर इसलिए बताऊंगी रैम रोम की जहां जहां जरूरत होगी, वैसे उसके लिए अलग से वीडियो होगी। विंडो को हार्ड डिस्क से रैम में लोड करती है रोम, फिर क्या होता है कि रैम से मेन प्रोसेसर इसे प्रोसेस करता है। मैं अगेन इसको रिपीट करती हूँ कि विंडो को, मैं इसे लिख दूं, विंडो को हार्ड डिस्क से रैम में लोड करती है रोम, ठीक है। विंडो हार्ड डिस्क के अंदर पड़ी है और हार्ड डिस्क से रैम में लोड हो रही है, और कौन लोड कर रहा है, रोम लोड कर रहा है, ठीक है। नेक्स्ट थिंग इज फर्मवेयर। फर्मवेयर क्या होता है, ये हमारे पास सिंपली हम कह सकते हैं फर्मवेयर को सेट ऑफ इंस्ट्रक्शंस, ठीक है। दिस इज सेट ऑफ इंस्ट्रक्शंस। अब हमारी मेन कहानी स्टार्ट होती है मेमोरी की, मेमोरी डिवाइसेस की। इसको गौर से सुने, जहां से कंफ्यूजन हो वीडियो को रिपीट करके सुने, नहीं समझ आता तो कमेंट कर दें। प्रोसेसर, ठीक है। प्रोसेसर हमारे पास क्या है, हार्डवेयर है। प्रोसेसर करता क्या है, ये सेट ऑफ इंस्ट्रक्शंस को प्रोसेस करता है। अब इसके अंदर जो मेन कहानी है, ये सेट ऑफ इंस्ट्रक्शंस आ कहां से रहे हैं। प्रोसेसर प्रोसेस कर रहा है सेट ऑफ इंस्ट्रक्शंस को। सेट ऑफ इंस्ट्रक्शन प्रोसेस के पास आए कहां से, सॉफ्टवेयर से। सॉफ्टवेयर सेट ऑफ इंस्ट्रक्शंस देगा प्रोसेसर को और प्रोसेसर इसे प्रोसेस करेगा। क्या हो रहा है अब इधर के सॉफ्टवेयर कम्युनिकेट कर रहा है प्रोसेसर के साथ। कम्युनिकेशन में क्या हो रहा है, सेट ऑफ इंस्ट्रक्शंस उसे दे रहा है। सॉफ्टवेयर को हम एक और क्या लफ्ज इसके लिए यूज कर सकते हैं, दैट कैन बी, वी कैन यूज द वर्ड विंडो, वी कैन यूज द वर्ड ऑपरेटिंग सिस्टम, ठीक है। अब हमारे पास रोम क्या कर रहा है, ये जो ऊपर बात बताई मैंने, रोम हमारे पास लोड कर रहा है सिस्टम को, लाइक ऑपरेटिंग सिस्टम को, सॉफ्टवेयर को फर्मवेयर का यूज करते हुए रैम में, कहां से, फ्रॉम हार्ड डिस्क, फ्रॉम हार्ड डिस्क। मैं इस बात को दोबारा रिपीट करती हूँ ताकि क्लियर हो। सेट ऑफ इंस्ट्रक्शंस का यूज करते हुए सॉफ्टवेयर लोड हो रहा है रोम में, सॉरी रैम में, फ्रॉम हार्ड डिस्क। इंग्लिश का जुमला बोलती हूँ, रोम इज लोडिंग द ऑपरेटिंग सिस्टम बाय यूजिंग फर्मवेयर इन रैम फ्रॉम हार्ड डिस्क। क्लियर है अब ये पॉइंट। इसको हम कहते हैं बूटस्ट्रैपिंग। रोम इज लोडिंग द सेट ऑफ इंस्ट्रक्शन, सॉफ्टवेयर को लोड कर रहा है, दिस इज बूटस्ट्रैपिंग। ये क्यों हो रहा है, अब टू इंक्रीज द परफॉर्मेंस ऑफ प्रोसेसर, इस प्रोसेसर की परफॉर्मेंस को इंक्रीज करने के लिए हमारे पास एक फास्ट मेमोरी रैम यूज हो रही है प्रोसेसर के साथ कम्युनिकेशन में। रैम क्या है? एक टेम्पररी मेमोरी है। ये हमारे पास, इसकी बात करते हैं थोड़ी सी। ये टेम्पररी मेमोरी है और ये क्या करती है? गिव और टेक डेटा टू और फ्रॉम प्रोसेसर। दिस इज द रिलेशन। टेम्पररी मेमोरी gives और take data from और to processor। अब हमारे पास आगे क्या बात आती है कि जो रैम है हमारे पास, जो कि हम यूज कर रहे थे, वो स्लो साबित हुई जब हमारे पास न्यू प्रोसेसर्स आए। सो फॉर द फास्ट कम्युनिकेशन वी यूज कैशे मेमोरी। वी यूज कैशे मेमोरी। बिटवीन, अभी कहाँ पे यूज हो रही है? बिटवीन रैम एंड प्रोसेसर। ठीक है, रैम और प्रोसेसर के दरमियान में एक और चीज इंक्लूड हुई, दैट इज कैशे मेमोरी। अब प्रोसेसर क्या करेगा? प्रोसेसर जो सेट ऑफ इंस्ट्रक्शंस ले रहा था, अब वो अपने सेट ऑफ इंस्ट्रक्शंस लेगा कैशे मेमोरी से। ठीक है, ये दरमियान में यूज हो रही है, किसके? रैम और प्रोसेसर के दरमियान में आ गई। कैशे मेमोरी क्या है? फास्ट है रैम से, लेकिन इसकी जो स्पेस है वो लेस है स्टोरेज स्पेस रैम से। फास्ट है रैम से बट स्टोरेज स्पेस कम है। अब हमारे पास क्या हुआ कि जब मजीद टेक्नोलॉजी आई तो हमारे पास कैशे मेमोरी भी स्लो साबित हुई। कैशे मेमोरी, हमारे पास रैम स्लो हुई थी तो हमने कैशे मेमोरी लाए थे। अब कैशे मेमोरी स्लो होगी तो एक न्यू चीज इंक्लूड हो रही है, रजिस्टर्स। ये बात याद रखी जाए कि हमारे पास रजिस्टर्स भी टेम्पररी मेमोरी है। अब हम रजिस्टर्स को इन बिटवीन यूज करेंगे कैशे मेमोरी के और प्रोसेसर के। कैशे मेमोरी और प्रोसेसर के दरमियान में एक न्यू चीज आ गई, दैट इज रजिस्टर्स। ये हमारे पास कैशे मेमोरी से फास्ट है, लेकिन इनकी स्टोरेज स्पेस कैशे मेमोरी से कम है। अब इसके बाद क्या हुआ? हमारे पास डिस्टेंस जो था ना प्रोसेसर का और रजिस्टर्स का, क्योंकि दरमियान में इतने सारे डिवाइसेस आ रहे थे तो हमारे पास डिस्टेंस जो है वो ज्यादा हो रहा था। अब इस डिस्टेंस को कम करने के लिए हमने क्या किया? कैशे मेमोरी और रजिस्टर्स को एक चीज बना दिया। ठीक है, इन दोनों को मिला दिया, कैशे मेमोरी और रजिस्टर्स को, और एक चीज बना दिया जिसे हमने कहा कि वो है IPM। ये जो इधर बताया था, इंटरनल प्रोसेसर मेमोरी। कैशे और रजिस्टर मिला के इंटरनल प्रोसेसर मेमोरी बना दिया और इसकी जगह पे वो लगा दिया। ये है हमारे पास सारी कहानी मेमोरी डिवाइसेस की, जो कि डिजिटल इलेक्ट्रॉनिक्स में यूज होती हैं। जोन सी डिवाइसेस? स्टोरेज, प्राइमरी, सेकेंडरी, रैम रोम, पेरिफेरल डिवाइसेस। मेमोरी में आ गया IPM, मेन मेमोरी, सेकेंडरी मेमोरी। मेन मेमोरी रैम रोम यूज हो रहे हैं। सेकेंडरी मेमोरी हमारे पास परमानेंट मेमोरी है, जो कि हमारे पास हार्ड डिस्क होती है, जहाँ पे सॉफ्टवेयर स्टोर्ड होता है, जहाँ से हम लोड करते हैं सॉफ्टवेयर को। और IPM क्या है? IPM हमारे पास कैशे मेमोरी और रजिस्टर को मिला के हमने एक डिवाइस बना दी। तो ये हमारे पास तीन मेमोरीज हैं, जो उनकी एक्सप्लेनेशन ये सारी है। अब अगर आपको कोई भी कंफ्यूजन है तो आप इसे कमेंट सेक्शन में पूछ सकते हैं। Today we will start our 12th lecture of the course Digital Electronics. In today's lecture we will study the latch. We have SR latch and we are using the NOR gate in it. Okay, so first we will draw the symbol of the NOR gate. This is the symbol of the NOR gate. Okay, and its truth table is, if we have input 0 0 0 1 1 0 1 1 1 0 0 0, To explain the truth table of the NOR, the simple we can say whenever we have 1 in the input, the output will be 0. We have to remember this rule on the fingertip to solve our SR latch in speed. So now we will draw the SR latch, the NOR gate, and the other NOR gate. One is for the S and one is for the R. SR means set reset latch. So this one and this one. Their outputs are Q and Q bar. This is S. This is R. S output is Q bar and the R output is Q. The one input is S and the other output is the output of the R. Other input, this is input S and Q. And for the R, we have the other input with R, which is Q bar, the output of the S1. Now we will make its truth table SR, Q and Q bar. We have 1 and 0. So when we have 1, this is 1, S is 1 and the R1 is 0. Okay. So we can see when we have one input, whenever we have one input, the output will be 0. So for this we can say the output of the S1 is 0. Q bar is 0. It will be the input of the R with R, the R has its own value 0. Q bar is 0. 0 and 0 will give us 1. So it means Q is 1. Now we will solve the second one. If the S is 0 and the R is 0. If S is 0 and R is 0, we can see that now we should know the other one input. So we can solve the NOR gate further. So now we will imagine that Q is 1. Okay, we are taking it by ourselves that the Q is 1. So whenever any of the input is 1, the output is 0. Q bar will be 0. Now we will recheck this one. 0 and 0, the output will be 1, that is Q. Now we will solve it again with 0 and 0. Now we will imagine that if in case the Q is 0. So if the Q is 0, the output will be 1, Q bar will be 1, and when 1 will go here, there is the 1, there is 0, the output will be 0, which is the value of Q. The next thing is if S is 0 and R is 1. If S is 0 and R is 1, so whenever any of the input is 1, the output will be 0. Q is 0, Q is 0 and S is 0, the output will be 1, Q bar will be 1. Now we have to see that if S is 1 and R is 1, then both the outputs will be 0. That the SR latch for the 1 1 is invalid. This is an invalid state, and for the 0 0 we will get the states, we call them hold state. For the 0 and 0, yes, these are the hold states. Now to solve this invalidity, we will study the SR flip-flop. This one was the SR latch in which we get the invalid value, and in SR flip-flop we will solve this invalidity. Today we will start our 13th lecture of our course Digital Electronics. In today's lecture we will study the JK flip-flop. In this lecture we will see that how can we make the circuit diagram of the JK flip-flop and its table. The diagram starts by the AND gate and we will have the NOR gate in it. Simply we can draw the AND gate first. This is our AND gate and it will be connected to the NOR gate. This is our NOR gate and we will repeat it again. AND gate and the NOR gate. These are our outputs, inputs, and as it is the flip-flop, the thing in flip-flop we have is that it has a clock in it. When we will trigger the clock, the circuit will start working. Next thing is, this is our J input, this is our K input. These outputs will be connected to the NOR gate as input and these outputs are also working as the input of the AND gate. So simply this is our complete circuit of the JK. This is our Q and this is our Q bar. So now we will start it as, this is our clock which will always be 1, J, K, Q and Qn plus 1. So whenever we will always take the clock 1 and on our first step we are taking J0 and K0 as our inputs. J and K both are 0. So as the clock is 1 and the first input J is 0, so it according to AND gate we can see that whenever our input is 0, the output will be 0 because it will multiply it. So 1 into 0 will be 0, so we will not consider the other input as if it is 1 or 0, the output will be 0 in any condition. So we will have 0 here and same we have 0 here. Now if we have 0 here, we have to see the other input, this one. So we will imagine that Q is equal to 0. So if both the inputs are 0, it means our output of the NOR gate is 1. So this is 1. Our output of the NOR gate is 1. So now this one will go here as input and from here we have the 0 input and 0 and 1. So it will give us 0 again. So this is our answer. Now we will repeat this step by taking the Q equal to 1. That if we imagine here the Q input is 1. So we have 0. This one input, now we are taking it 1. It will give us the 0 output. Now this is 0. This 0 will go here and we have 0 input, 0 and 0 will give us 1. So this is our answer 1. On the next step we are taking it as clock is always 1. We are taking J equal to 0, K equal to 1 and we will take it as 0. So now whenever J is 0 and K is 1. So it says that when J is 0, 1 and 0 will be 0. It is 0 and now we should know the other input, so we will process it further. So now we will see that now we are taking it as 0. So this is 0, this is 1, clock is also 1. So when this 0 will go here, so we will, according to the AND gate, we will get the answer 0. So we are taking 0 here, it will be 0 and 0 will give us 1. 1 will go here as the input and we have 0 already and 1 and 0 will give us 0. So our answer will be 0. So on the next step now we will take it as the 1. Then if we repeat all the values, 0 and 1, and we are imagining the value of the q as 1. So now we will again do it, that if our j is 0 and k is 1, we are taking q equal to the 1. This is 1. So here we have the input 0. The other input is 1. And we will here get 0 answer. This 0 will go here as the input 0. And from here we have 1 and 1. And the other input we are also taking 1. So it will give us the 1 input. 1 and 0 will give us the 0 output. So our answer is 0. Now we will see that whenever clock is 1, we are taking the value of j and k as j is 1 and k is 0. So now we will see that whenever we will take our input q as 0, so our j is 1, k is 0, and our q input is 0. Here we have 0. Okay, now we have 1 and 1. So we should know the other input, and so for this we are imagining our this input as 0. So it means its q bar, it should be the opposite of this. So this is 1. Okay. So when we will take it as 1, these all three 1 will give us 1. The other input is 0. 1 and 0 will give us 0. Here we go, the input is 0. Here our k is 0 and the clock is 1. So 0 and 1 will give us 0. 0 and 0 will give us 1 output. So here our output is 1. Now we will take these values again. 1, 0, but this time we will take q equal to 1. So whenever our q is equal to 1, it means our q bar is equal to 0. Our q is 1, so it means q bar is 0. Here we have 1, 1, and this q bar equal to 0. So it will give us the value 0. This one is 1, 1 and 0 will give us 0. Here we go, the 0 is our input. Here the value of the k is 0. This one is 1 we have and 1. It will give us 0 according to AND gate. 0 and 0 will give us 1. So here we will have 1. The next one is that we will take it as clock 1, J1, and we will take k also equal to the 1, and now we will imagine the values of q. If we take the value of q is 0, if the value of q is 0, so we have clock 1, J1, so we should know the other value. If this is 0, it should be 1. This is 1, so all 1 will give us 1. And here we have the value 0. 1 and 0 will give us 0. This 0 will go here as input. And on this k we have values 1. K is also 1. And we imagine the value of q as 0. So it will give us 0. 0 and 0 will give us 1 output. We will do it again by taking the value of the k, value of the q 1. So when this q is 1, it means this q bar is 0. We have J1, we have clock 1, and this q value is 1, it means this one value is 0. Here we have 0, it will give us 0 value. This one is 1. 1 and 0 will give us 0. Here we go, it is 0. And for this k we have 1, clock is 1, this value is also 1, it will give us the 1. 1 and 0 will give us 0. So this is our answer, 0. So now we will name these states. The first one state is, we call it the previous state. The next one 0 and 1. When we have q0 and qn plus 1 0, this is our reset state. this is our set state, and when we have 0 and 1 and 1 and 0, these are our toggle states. So now this is our JK flip-flop, and I have explained it completely. This is its diagram, and this is our table which we made by the circuit diagram by processing our JK values and the Q values. Qn plus 1 is our result. And this is the clock which should be trigger 1, so our circuit will work. If it's 0, our circuit will not work. We will not get any value. In today's lecture, we will study the D flip-flop. This is our 14th lecture of our course Digital Electronics. Our D flip-flop starts as same as the JK flip-flop. First of all, we have the AND gate, and it is connected with the NOR gate. This is our NOR gate, and we will have the output. We will repeat it again. We will have the AND gate. It is connected with the NOR gate, and we will have our output. The next step is these outputs are the inputs of the NOR gate, like this. This one also is the input of the NOR gate, and here we have the clock connected with both of them, both of our AND gates. And then the main thing of the D flip-flop is we have the input D here, which is connected with both AND gates as, on the first it is same, but for the second AND gate it is connected by passing from the NOT gate. Okay, this is our Q, and this is our Q bar, the opposite of this one. So now it will work as, we will have our clock here, the D, Q, okay, and Qn plus 1. Our clock will always be 1. AND gate do the multiplication, NOR gate will give us the value, equal to the 0 whenever we have any of the value or input 1, and the NOT gate will convert the value, will opposite the value. If we have 1, it will be 0, and if we have 0, it will be 1. So for the D, we are taking 0, and we are imagining our this value Q as 0. So we have this 0. Okay, so this is 0. Process it as B is 0. We will have 0 on this input. The clock is 1. 1 and 0 will give us 0. And when this 0 will pass from the NOT gate, it will be converted to the 1, and 1 and 1 will give us 1. We are taking it as 0. So both 0 will give us 1. 1 and 1 will give us 0. Our final answer is 0. Now we are taking D 0, but Q as 1. We are taking the Q as 1. So when we have 1 here, it will give us 0. This 0 and this 1 will give us again 0. We will have 0 in this output also. This is our reset state. Now we will have the value of the D as 1, and we will imagine the value of the Q as 0. जब हमारे पास D भी 1 है और Q 0 है, okay, जब हमारे पास D 1 है और Q 0 है, D हमारे पास 1 है, तो it means इधर हमारे पास input 0 होगा, क्योंकि NOT gate से पास हो रहा है 1, and 1 will give us 1 passing from the AND gate. The other input, we are imagining Q is equal to 0. So 0 and 1 will give us 0. Here we have the input 0. And from here we have 0 and 1. The input 0. 0 and 0 will give us 1. Here we have Qn plus 1 equal to 1. For the other one, we are taking the Q as 1. We have 1 here. So 1 and 1 will give us 0 again. We have 0. For this we have 0. and 0 will give us 1 again. So this is our set state. This is the 14th lecture of our course Digital Electronics, in which we have studied the D flip-flop. In our next lecture, we will study the T flip-flop. This is our 15th lecture of our course Digital Electronics. In this lecture, we will study the T flip-flop. For this, we will start from the AND gate, which is connected with the NOR gate, and we will have the output. We will repeat it again. AND gate connected with the NOR gate and the output. Here we have the T input as like this. We will have the clock. Now these outputs are connected with the NOR gate as input like this, and these outputs are also the input of the AND gate. Now we will start its working. This is our Q bar. This is Q. We will take it as clock, which is always 1, T, Q and Qn plus 1. We are taking the clock equal to 1, T equal to 0 and Q equal to 0. So when our T is 0 and Q is 0, so here we have 1 and 0, it will give us 0. 0 and 0 will give us the output 1. This one will go here as input, and we have T equal to 0, so automatically the AND gate will give us 0. This 0 and 1 will give us output 0. Here we have 0. For 1, 0, when we are imagining the Q as 1, we are taking it as 1. Here we have 1. The other inputs will remain same. 1 and 0 will give us 0. This 0 will go here. 0 and 0 will give us 1. Here we have 1. Now we are taking the clock 1, T1 and Q equal to 0. When clock is 1 and T is also equal to 1, it means we should know the third input. If it is 0, our answer will be 0, and if it's 1, our answer will be 1. So as we are taking the Q equal to 0, it means our Q bar is equal to 1. So our all inputs are 1. Here we get the 1. This Q is 0. 0, 1 and 0 will give us 0. Here we have 0 input, and we have clock 1, T1 and Q equal to 0. So according to the AND gate, we will have 0. 0 and 0 will give us 1 output. We will have 1 here. Now we will take the clock 1, T1 and Q also equal to the 1. So when Q is 1, Q bar will be 0. This 0 will go here as input 1, 1 and 0. It will give us 0. This Q is 1. So this Q is 1. So 1 and 0 will give us 0 output according to the NOR gate. Here we go, we have 0 input, and for this we have clock is 1, our Q is 1 and T is also 1. So it will give us 1. And 1 and 0 will give us output 0. This is our T flip-flop, in which these are our hold-on states, and this is our toggle state. This is how our T flip-flop works. Today we will start our 16th lecture of course Digital Electronics. In today's lecture we will study shift registers. It has 4 types: serial input, serial output, serial input, parallel output, and parallel input, parallel output, and parallel input, serial output. These are the 4 types of the shift registers. We will start our today's lecture from serial input, serial output register. In this, we will have the serial input and the serial output. Our input is from this side. This is our input, and on the Q and 0 or Q and 0 we will get our output. This is the clock which is connected. We will have the clock, then our clock is 1, like we are giving the first clock and our process starts. This 0 will be input and it will go at the place of Qn3. First of all, we will write it as Qn3, Qn2, Qn1 and Qn0. On the clock 1, our 0 will be the input at the place of Qn3. This is our input, and the other inputs are that Qn3 will move forward, Qn2 will move forward, and Qn1 will move forward. So we will have Qn3 here, Qn2 and Qn1. After that, when we will give the second clock, our 0 will move forward and the 1 will be the next input at the place of 0, and 0 will move forward to the Qn2, Qn2 will move forward to Qn1, here we have Qn3, and then we have Qn2. After that, we will give our third clock, so our 1 will move forward, 0 will move forward, Qn3 will move forward, and at the first place we will have 1 input, this one, and after that we are only left with the 0 here. So on the fourth clock, 0 will move forward, all the values will step forward, 1, 1 and 0. So as we have serial input, serial output, so after 4 clocks we have the output 0, as we have the serial output. So serial, when we will go serial wise, we will have the output 0 after 4 clocks. On the 5th clock, as we have this as the output, our this one will move forward, this one will be here, and this 0 is here. On the 6th clock, here we have this one output. On the 6th clock, this one will move here. This is our third output on the 6th clock. And on the 7th clock, this 0 will be at Qn0, our output. So this is our final answer, 0, 1, 1, 0, which we have given the input. From here we can see that as we have n equal to 4, the total clocks we are using are 2n minus 1. That is 2 into 4 minus 1 is equal to 7. Total 7 clocks we are using. After that we will have, now we are having serial input parallel output register. In this register we are having serial inputs but the parallel outputs. Serial inputs but the parallel outputs. So for this we are taking our value 0, 1, 0, 1. As the clock is 1, our Qn3 will move forward, Qn2 will move forward, Qn1 will move forward. Why? Because at the place of Qn3 on the clock 1, as the clock is triggered, we will get our first value as our Qn3. So here we have 1. On the clock 2, 1 will move forward, Qn3 will move forward, Qn2 will move forward, and at the place of 1, now we are having our next input, that is 0. On clock 3, we will have our next input, that is 1. This 0 will move forward, 1 will move forward, and Qn3 will move forward. Now we are having Qn3 at this place. For the 4th clock, our 0 will be our next input, we will have 0, 1, 0, 1. Now we are having our all values 0, 1, 0, 1 as the output on the 4 clocks. As it is the serial input parallel output, different from the serial input serial output. As we have the parallel output, so parallelly we are getting all these values as our final answer output. As on the 4 clocks total, we will get our output. It is faster than serial input serial output register. Now we have parallel input serial output register. In this register, we have the parallel inputs. So we are taking the value 0, 111. As we have parallel input, so our first input is 0, 1, 1 and 1. We can give the parallel inputs. Now at the clock 1, we have all these values. As the clock is triggered, we will get all of these as the input. So 0, 1, 1, 1. On the clock 2, why we are using the clock 2? Because these are the parallel inputs but the serial output. On this output, we are having 1 at this time. Now to get all the values at the output, we have to do the other clocks also. So for the clock 2, this 0 will move forward, this 1 will move forward, this 1 will move forward. So on the clock 3, we will have, as we have this one here output, this one is output here, now this one is output here, and we are left with our only 0, and when we will give the 4th clock, this 0 will move to the final answer like this. Now we are having this 0 at the output. So this is our final answer. On the 4 clocks, we are getting our answer. That is 0, 111. This is our parallel input but serial output register. This is our 4th register, that is parallel input parallel output register. We are taking our value as 1101 as it is the parallel input and the same input we have as for the parallel input serial output. So for the input we will have 1, 1, 0, 1. This one is getting here as the input, this one is here as the input, this 0 is here as the input, and this 1 is here as the input. As we have the parallel output, so for this, on the clock 1, when the clock 1 is triggered, our inputs are 1, 1, 0, 1 on the clock 1, on the first clock. But as it has the parallel output, so as the 1 is entered, it will be the output. We will have it at the output. This 0 and this 1 will be at the output. So this is the fastest of all the 4. The parallel input parallel output is the fastest register. That on the first clock we will get all our outputs ready to use. 1, 1, 0, 1 is our final answer. So these are the 4 types of the registers.